Your Oracle execution plan is lying to you? Yes, lying. Have you ever seen a query that looks absolutely perfect in the execution plan but takes 30 seconds, 60 seconds, or even minutes in production? You check the plan, the cost looks low, the access path looks good, everything appears correct, yet the query is painfully slow. So, what is going on? Is Oracle broken? Is the SQL bad? Or is the execution plan hiding something from you? In this video, I will show you a live Oracle demo where the execution plan tells one story, but reality tells a completely different story. Let's get started. But before we dive into the demo, let me quickly introduce myself. Hello everyone, welcome back to the channel. This is Sanjai Kumar. I have spent more than 15 years working on Oracle production systems, handling performance tuning, Severity 1 incidents, rack environments, data guard, and critical database troubleshooting for enterprise systems. And today, I am going to show you one Oracle performance tuning truth that most DBAs learn the hard way. If you are an Oracle DBA, developer, performance engineer, or anyone involved in SQL tuning, this is a lesson you cannot afford to miss. Agenda of the video. In the next few minutes, I will show you why explain plan can mislead you, why display cursor sometimes fails, how to collect actual runtime statistics, how histograms affect cardinality estimates, and how to identify optimizer mistakes in production. Problem setup. I have seen this again and again in production. Developer says execution plan looks good. DBA says optimizer stats are fine, but production is still painfully slow. Why? Because people trust explain plan blindly. And here is the truth nobody talks about. Explain plan shows what Oracle thinks it will do, not what Oracle actually did. Core concept. These are two completely different worlds. Explain plan is based on optimizer estimates, statistics, assumptions, but real execution depends on data skew, histograms, bind variable behavior, cardinality estimates, runtime conditions, and when Oracle guesses wrong, performance problems begin. Real production example. Imagine this scenario. Estimated rows equals 1. Actual rows equals 4.2 million. What happens? Because Oracle believes only one row will be returned, it chooses a nested loop join. From the optimizer's perspective, that decision makes perfect sense. But in reality, the query returns 4.2 million rows. And for that volume of data, a hash join would have been a much better choice. Now, your query explodes from milliseconds to minutes. Simple analogy. Think of it like a supermarket. Oracle is the store manager. Based on its estimate, Oracle believes only one customer is coming. So it opens just one checkout counter. Everything seems fine, but suddenly 4.2 million customers walk through the door. Now that single checkout counter becomes a huge bottleneck. Queues grow longer and longer. The entire store becomes overloaded. I have actually seen this happen in a production environment. During my database support career, I worked on a severity 1 performance issue where a critical query suddenly started taking more than 40 seconds to complete. At first glance, the execution plan looked perfectly fine. Statistics were up to date. Nothing appeared unusual. But when I checked the actual execution statistics using display cursor, I discovered something interesting. Oracle estimated only a few hundred rows. In reality, it processed millions of rows. That huge gap between the estimated rows and the actual rows completely changed how the optimizer viewed the query. And that single observation led us directly to the root cause of the performance problem. Here is the one command that reveals the truth. We are using dbms explant.display cursor. This shows the actual execution plan Oracle used during runtime. Here we pass the SQL ID of the query we want to analyze. This tells Oracle, show me the execution details for the specific SQL statement. This command shows actual execution plan, runtime statistics, actual rows processed, real execution behavior. This is production grade tuning. When you run this command, focus on these two columns, estimated rows, actual rows. If Oracle estimated one row but processed 4 million rows, that is your bottleneck. Now, let's prove this with a real demo. To demonstrate the problem, I am going to create a simple table called orders underscore demo. This table contains three columns: order ID, customer ID, order status. Once the table is created, I will load it with the data that is intentionally skewed. Step 1, create demo table. First, let us create our demo table. As you can see, it is a simple orders table with an order ID, customer ID, and a status column. Step number 2, insert skewed data. Now comes the important part. I am going to insert more than 1 million rows into this table. But here is the trick. Almost every row will have the status value active. Only a very small number of rows will have the status value inactive. This creates what is known as a skewed data distribution. In real production systems, skewed data is very common, and it is one of the main reasons why Oracle's cardinality estimates can become inaccurate. Let's load that data now. Once the data is loaded, we have approximately 1 million active rows, 100 inactive rows. This is exactly the type of data distribution that can confuse the optimizer when histograms are not available. Step number 3, create index. Next, Let us create an index on the status column. Why? Because we want to give the optimizer a choice between using an index scan and a full table scan. At this point, everything looks perfectly normal. Step number 4, gather statistics without histogram. Now comes the interesting part, and this is where many performance problems begin. We are going to gather optimizer statistics on the table, but we are intentionally going to do it without creating histograms. Notice this parameter. This tells Oracle to collect basic statistics, but not create histograms on any column. And that is the trap. Without histograms, Oracle has no visibility into how values are actually distributed inside the column. Instead, Oracle assumes that the data is distributed evenly across all values. But in our case, that is completely wrong. Remember, our data active equals 1 million rows, inactive equals only 100 rows. This is highly skewed data. Yet, Oracle does not know that. Without a histogram, the optimizer assumes a uniform distribution and starts making cardinality estimates based on that incorrect assumptions. And as you will see in the next step, that wrong assumption can lead to inaccurate estimates and potentially poor execution plans.
Explain plan demo. Now let's see what Oracle thinks about this query. We will start by generating an execution plan using explain plan. And then display the plan using dbms underscore xplan. Now look carefully at this output. The estimated row count looks reasonable. The execution plan looks efficient. The optimizer seems confident. Everything appears perfectly fine. And that is exactly where many TBS get fooled. What is actually happening? At this point, Oracle has not executed the query. It simply asks the optimizer, if I execute this query, what plan would you choose? Based on the available statistics, Oracle generates a hypothetical execution plan. Estimated cost, which is 790. Estimated row counts, which is 5 lakhs. But remember, the query was never executed. No rows were actually processed. No runtime statistics were collected. No actual rows are available. No real execution metrics exist. So, what you are seeing is the only optimizer's prediction. Now, let us execute the query for real or actual number of rows in the table. This query actually runs and processes the data. The result shows there are approximately 1 million active rows in the table. Important observation. Now compare that with Oracle's estimate. Oracle estimated 5 lakhs rows, but the actual number of rows is 1 million rows. That means the optimizer underestimated the cardinality by 2 times. And this is the heart of the demo. The execution plan looked perfectly fine. The estimates looked reasonable. But the optimizer's prediction was significantly different from reality. And when row estimates are wrong, Oracle can easily choose the wrong execution plan, leading to serious performance problems in production system. Now that we have actually executed the query, the Oracle has created a real cursor in memory. The next step is to find the SQL_ID associated with that execution. Here I am querying the $SQL view. And searching for statements that reference the orders_demo table. I am sorting by last_active_time. So the most recently executed SQL appears at the top, and there it is. Oracle returns the SQL_ID for the statement we have just executed. This is the actual cursor created during the execution, not the explain plan statement. Key point. Remember, dbms_explan.display_cursor can only display execution statistics for a real cursor. That's why finding the correct SQL_ID is so important. Without the SQL_ID of an execution statement, there are no runtime statistics to analyze. Now, let us make a very common mistake that many DBAs make. Here I am using dbms underscore xplan dot display underscore cursor, which is designed to display the execution statistics of a real SQL cursor. And Oracle returns an error for the SQL underscore ID associated with the explain plan statement. Cannot fetch plan for SQL underscore ID. This SQL ID is associated with an explain plan. At first glance, this can be confusing. After all, we just generated an execution plan using explain plan. So why cannot display underscore cursor find it? Why did this happen? Because explain plan does not actually execute the SQL statement. When we ran explain plan for select star from demo dot orders underscore demo, where status is equal to active, Oracle simply asked the optimizer, if this query were executed, what plan would you choose? Oracle then generated an estimated execution plan and stored it in the plan underscore table. However, this SQL statement itself was never executed. As a result, no SQL execution occurred. No cursor was created in memory. No runtime statistics were collected. No actual rows were generated. No execution metrics were captured. And because there is no real executed cursor, display underscore cursor has nothing to display. Powerful teaching line. This is one of the most important concepts in Oracle performance tuning. Explain plan does not execute the SQL, does not collect runtime statistics, does not capture actual execution metrics, does not show what actually happened during execution. It only shows what the optimizer thinks might happen. Remember this, explain plan is a prediction, display underscore cursor is reality, and when you troubleshooting performance problems, reality is what matters. Now let us do it the correct way. If you want real execution statistics, Oracle must actually execute the SQL statement. And to capture those runtime statistics, I am using the gather underscore plan underscore statistics hint. This time everything changes. Unlike explain plan, Oracle is no longer simulating the query. Oracle is actually executing it. As a result, Oracle now executes the SQL statement, creates a real cursor in memory, collects runtime execution statistics, captures actual rows, records logical and physical IO activity, tracks buffer gates and other execution metrics. Now that Oracle has actually executed the query and collected runtime statistics, the next step is to find the SQL underscore ID associated with that execution. To do that, I just queried the v dollar underscore SQL view, which contains information about SQL statements currently stored in Oracle's shared pool. Here I am searching for SQL statement that reference the orders underscore demo table and sorting them by last active time, so the most recently executed SQL appears at first, and there it is. Oracle returns the SQL ID. This is the SQL ID of the real executed cursor, not the explain plan statement. Now that we have the correct SQL ID, let us see what actually happened during execution. To do that, I will use dbms underscore explan dot display underscore cursor, which shows the real execution statistics collected by Oracle. This time, Oracle successfully displays the execution plan along with the runtime statistics. And now we can compare what Oracle estimated versus what actually happened. Oracle shows estimated rows 5 lakhs, actual rows 1 million. So estimation here, estimation error 100%. What does this mean? The optimizer estimated that the query would process about 5 lakhs rows, but at runtime Oracle actually processed 1 million rows. That is a 100% estimation error. In other words, the optimizer's estimate was significantly different from reality. Why did Oracle misestimate? The answer goes back to the statistics we collected earlier. Remember this statement: using for all columns size 1 tells Oracle not to create histogram. Without histograms, Oracle assumes that data values are distributed evenly across the table. However, our data was heavily skewed. Active equals 1 million rows, inactive equals 100 rows. Since Oracle did not have histogram information, it could not see this skewed distribution. As a result, it made a uniform distribution assumption and produced an inaccurate cardinality estimate. Key lesson: without histograms, Oracle cannot recognize data skew. Cardinality estimates can be inaccurate. The optimizer may choose a suboptimal execution plan. Now, here is another situation that confuses many Oracle DBA. Suppose you execute a query like this. The query runs successfully. So naturally, you expect Oracle to have captured all the execution details. Next, you run dbms underscore xplan dot display underscore cursor to see the actual execution statistics. But instead of seeing actual rows and runtime metrics, Oracle displays this warning. Basic plan statistics not available. What does this mean? This warning does not mean the query failed. In fact, Oracle executed the query successfully. The problem is that Oracle did not collect runtime execution statistics for that cursor. As a result, Oracle cannot show actual rows, actual starts, actual buffers, actual runtime metrics. So display underscore cursor can only show the estimated execution plan. Not what actually happened during execution. So why did not Oracle collect the runtime statistics? Because Oracle only captures detailed execution statistics when one of the following condition is met. The query uses the gather underscore plan underscore statistics hint, or the session is configured with alter session set statistics underscore label equals on. Key lesson: executing a query alone is not always enough. If runtime statistics are not collected, Oracle will display warning basic plan statistics not available. Without runtime statistics, you cannot compare estimated rows versus actual rows, which means you may miss the real cause of a performance problem. So far, we have seen why Oracle misestimated the number of rows. The root cause was not the execution plan itself. The real problem was that Oracle did not have enough information about the data distribution in the status column. Now let us fix that. What does this mean? Earlier we gathered statistics using for all column size 1, which prevented Oracle from creating histogram. This time we are telling Oracle to create a histogram specifically on the status column. Why is a histogram important? A histogram allows Oracle to understand how data is actually distributed inside a column. Instead of assuming all values occur equally often, Oracle can now see the real frequency of each value. For our table, active equals 1 million rows, inactive equals 100 rows. Oracle can now clearly recognize that the data is highly skewed, and that is exactly the information the optimizer was missing. After creating the histogram, Oracle understands data skew. Cardinality estimates become more accurate. Estimated rows move closer to actual rows. The optimizer can make better execution plan decision. The risk of choosing an inefficient access path is greatly reduced. When cardinality estimates are wrong, don't immediately blame the optimizer. First ask yourself, does Oracle understand the data distribution? Because in many real world performance issues, the solution is not changing the SQL. The solution is giving the optimizer better statistics. Now rechecking the execution plan. Now that we have created a histogram on the status column, let us run the query again and check the execution plan one more time. Notice what happens now. This time Oracle has much better information about the data distribution, and the cardinality estimate becomes far more accurate. Before histogram, estimated rows equals 5 lakhs, actual rows equals 1 million. Earlier, Oracle estimated only 5 lakhs rows, while the actual execution processed 1 million rows. The optimizer was making decisions based on incomplete information. After histogram, after gathering statistics with a histogram, Oracle can see that almost all rows contain the value active. As a result, the estimated rows move much closer to the actual rows. What is different now? The SQL statement has not changed. The index has not changed. The application has not changed. The only thing we changed was the optimizer statistics. By providing Oracle with a histogram, we allowed the optimizer to understand the real data distribution instead of assuming a uniform distribution. Final takeaway. Before we wrap up, let us summarize the most important lesson from this entire demo. If you remember just one thing from this video, make it this. Explain plan shows what Oracle thinks it will do. Display cursor shows what Oracle actually did. And when you are troubleshooting performance problems, what actually happened is far more important than what Oracle predicted. Throughout this demo, we saw how Oracle estimated 5 lakhs rows while the query actually processed 1 million rows. We also saw how missing histograms caused inaccurate cardinality estimates and how comparing estimated rows with actual rows revealed the real issue. Key lessons. Explain plan does not execute SQL. Explain plan does not show runtime statistics. Display cursor requires a real executed cursor. Always compare estimated rows with actual rows. Histograms can dramatically improve cardinality estimates on skewed data. Final thought. Oracle performance tuning should never be based on assumption. It should be based on evidence, and that evidence comes from real execution statistics. Because in Oracle tuning, explain plan is imagination, display cursor is reality, and Oracle performance tuning starts with reality. Wrap up and CTA. And with that, we are going to wrap up today's video. Let us quickly recap the most important lesson. Explain plan shows what Oracle thinks it will do. Display cursor shows what Oracle actually did. As Oracle DBAs, we should never rely solely on estimated execution plans. Always validate your findings using real execution statistics whenever possible. Remember, a beautiful execution plan does not always mean a good execution plan. The real story is revealed only when you compare estimated rows with actual rows and analyze what happened during execution. If you have ever been misled by an explained plan during SQL tuning? Type plan in the comments below. I would love to hear your experience and how you discovered the real issue. And if you are interested in practical Oracle DBA tutorials, SQL tuning techniques, performance troubleshooting, optimizer internals, RAC, DataGuard, PostgreSQL, MySQL, and real world production support scenarios, make sure to like, share, and subscribe to the channel. Thank you for spending your time with me today. I will see you in the next video. Until then, keep learning, keep tuning, and happy database administration.